about the assignments or anything like that. By now, we're, what's the story? We are now sort of started talking about graph theory. Last class, we started talking about graph theory. In the back of the room, you will find the last assignment for the semester, okay, which is going to be on graph theory. There's the one thing to keep in mind is that it's a one-page assignment, except for the fact there's one little problem that didn't fit on the back of the page. So make sure you get all 7 problems. You know, you can work on that. That's due April 27th, which is sort of not for a couple weeks, so don't worry immediately about it. But we'll put that away. Any questions, one way or another? Several people have been coming by and starting to discuss people hopefully have firmed up what they're doing their projects on. Okay, if you have any questions about your projects, don't be afraid to come and talk to me. I will warn you that I will be away next week. Okay, so I will be here today and tomorrow. I will be out of town next week. Professor Bender will be covering my lectures. Okay, that's why I was showing him the equipment. Okay, and so he'll be covering. He has all my slides. He will be covering that, and he knows a lot about graph theory. So I think he'll be a good person to take over. So next week there'll be Professor Bender. I'll be out of town. If you need to discuss something with me, you can send me mail, although I'm likely to be out of email contact. I don't guarantee it, but likely to be out of email contact. Then I'll be back for another week. For the last week of lectures, I'll then be giving the last week of lectures. Then we've got the project presentations. So you should start thinking a little bit about your projects. And if you're if you're starting to be confused about your project or need more material, if you know you need more material, talk to me after class or tomorrow. And if not, make sure you talk to me early the week after I get back. Okay, so you have time to think about that. Any other project questions or other oriented questions?
I just wonder, when you're away, will Professor Bender hold office hours?
Will Professor Bender hold office hours? Professor Bender will hold Professor Bender's office hours. So, which means he will have office hours, but they will be at a different time. What I recommend you do is ask Professor Bender what his office hours are when he's here. It's probably on the web. It's if you know, but talk to him. He's actually quite accessible. So I encourage you to track him down if necessary. Okay. Any questions? Again, I'm sorry about the fact that I'll be out of town. Any other questions, one way or another? Question.
Purposes to use for the graph theory?
Okay, for graph theory, my favorite graph theory book, okay, is Doug West's Introduction to Graph Theory. Okay, this was the optional book listed at the beginning of the semester. So if you look for a graph theory book, this one I would like. Most of what we're covering in graph theory is pretty standard material, and in any graph theory book that you see, you're likely to find what you're looking for. Okay, so I recommend that you look at, in the library, there's lots of other graph theory books you'll find. Many of them will be in the math library if you need to find them. Some of the older graph theory books that are good, there was a book by a guy named Harari, there's a book by Bondi and Murty, there's a book by Chartrand. There's lots of books on graph theory, okay, and you can pick whichever one you want. But this is my favorite. Any questions? And if not, a lot of certainly to do the homeworks, I don't think you need more material than is in the notes for the homeworks. But you may want to follow up on that just to get some more help. Any questions? Okay, that's it. Let's now start lecture 20 on graph theory. Last class we talked about degrees, vertex degrees, and degree sequences, degrees of graphs. What I'd like to talk about now is a different kind of property of graphs that is very important, which is a property of connectivity. And the question of whether a graph is connected, to first thought, it seem like a fairly trivial matter. Okay? So, for example, in this kind of silly picture here. Here we have a turkey. This turkey is in one piece. This turkey is connected. This guy has an axe, chops off the turkey's head. The turkey is now in 2 pieces. The turkey is disconnected. Okay? So the question of whether a graph is connected is really the question of whether it is in one piece. Okay? And that would seem like a fairly trivial thing to decide. There are a couple of issues that make the question of connectivity much more interesting, however. The first is, what do we mean when, by whether a graph is connected, when we talk about a directed graph instead of an undirected graph? Okay? And the other thing is, can we, instead of talking about connectivity as a yes-no question, is it possible to talk about graphs in a way of saying that one graph is maybe more connected than another graph? Okay? And so these two questions enable us to ask a lot more interesting properties of things related to connectivity. Okay? Any questions about that? We say that a undirected graph is connected if there exists a path between every pair of vertices in the graph. Okay? And that, I think, will coincide largely with this definition is maybe a little bit different on the face of it than saying that it's in one piece. Because if you look at this is talking about paths. It's not talking about pieces. But of course, the important thing to see is that if you have two pieces, there is no path from here to there. Okay, so it is a reasonable way to define connectivity to talk in terms of paths. Okay, we say that its undirected graph is connected if there's a path between every pair of vertices. Now, directed graphs, there's two different ideas of connectivity that people typically talk about with directed graphs because of this, and what they are makes sense if you understand the path definition. Okay? We say that a directed graph is strongly connected if there's a directed path between every pair of vertices. We say that a graph is weakly connected if it would be connected ignoring the directions of the edges. Okay? That's really what the difference is. Strongly connected means that there's a directed path between every pair of vertices. Weakly connected means there is some kind of path if you ignore the edge directions. So let's look at some examples. The first graph, let's zoom it in here. This graph here, I claim, is weakly connected. Why is it weakly connected? Okay. If we ignore the arrows, okay, I think it's fair to say that there is a path from every vertex to every other vertex. Okay, in fact, if you look at it, if we ignore the arrows, there is one cycle on the outside. This cycle alone is enough to certainly prove that if we ignored the directions of the arrows, just the outside cycle of 5 edges would be enough to establish it as weakly connected, right? We could drive from here and get back home. Okay? In fact, actually, between every, even if we sort of delete these 3 edges and ignore the arrows, what we have would be weakly connected. Why? I could drive from any one of these vertices to any one of those vertices. And likewise, I could drive from any one of these vertices to any one of those vertices along the outside track. So sure enough, the weakly connected definition, this graph is weakly connected. Okay? How many people, any questions about that? Let's start things out. So weakly connected means that if we ignore the thing. Now, any graph that is strongly connected might be weak, is definitely going to be weakly connected. But just because you've got an undirected path between 2 vertices does not mean that you also have a directed path. If you look over here, this graph is not strongly connected. Why? There is no way to go from vertex A to anywhere. Correct? I can go from vertex, can I go from vertex D to anywhere? Yeah, I can go from D to E, D to C, D to B, D to A. So from vertex D, I can get to anywhere. Okay? From any vertex C, D, and here, these I can get to anywhere. From vertex E, I can only get to vertex A. Okay, so this is not strongly connected. Okay, this one, on the other hand, is strongly connected. Why? Well, again, actually, if you look at it, I've got this outer loop now is a directed loop. So I could drive just by taking the outer track, the outer, I can drive the outer roadway, okay, and go from any vertex to any other vertex, okay? So the important point here to keep in mind is that any strongly connected graph, by definition, has to be weakly connected, okay? Because if there's a directed path between every pair of vertices, then there's also a directed path if you, a path if you ignore the arrows. Okay, but it's not necessarily true the other way. Okay, so let's think about it. Okay, let's think about Manhattan. Okay, in Manhattan, you've got a lot of one-way streets. Okay, is Manhattan a one? So you can think about the underlying graph defining the roads in Manhattan. Okay, is Manhattan the road network strongly connected or weakly connected? Okay. Some people say strongly connected. Okay. Some people say weakly connected. Well, everyone should say weakly connected, because by definition, if it's weakly connected, if it's strongly connected, it has to be weakly connected. Okay. It's somehow one is a stronger term than the other. Okay. So it's sort of saying like is somebody at least 5 feet tall if they're 7 feet tall? The answer is yes. Okay? So the answer is the road network in Manhattan is weakly connected. It also, fortunately, happens to be strongly connected. What would be the problem if it was not strongly connected? You could drive into a situation where you could get your car someplace, but you couldn't get it home. Okay? At least not legally. Okay, now that might not faze a lot of New Yorkers. Okay, you could always just drive it but the fact that it's weakly connected means that you could drive it illegally home. Okay, if it was disconnected, unless your car could swim, okay, there's no way you could get it home, whether you ignore the signs or not. Okay, that's really the difference in the definitions. Any questions? Okay, good. So let's talk a little bit now about, suppose, let's say you want to design a road network. Okay, let's say we had the following situation. Okay, suppose, let's say I have a bunch of cities or intersections, if you wish. I have a bunch of roads. Each road is only wide enough for one lane of traffic. Okay, so I can't have two. You can move either, from left to right or right to left, but not both. Okay. The question I now give you is, given a undirected graph, is there always a way to assign each edge either a direction from either to the left or to the right so that we leave the graph strongly connected? My first question is this: if I give you an undirected graph, is there a way to orient the edges one way or the other to leave a weakly connected graph? Okay, suppose all I want is that the road network at the end be weakly connected. Can somebody give me a way to assign the edges arrows so that the graph is weakly connected? Well, if I want it to be weakly connected, I have to do anything. I just put up signs randomly, which I think may have been the algorithm they used in New York. Okay, don't know for sure. Okay, but that would certainly suffice. Okay, but the more interesting question is, given an undirected graph, can I orient the edges so that, in fact, it's strongly connected? Let's stop to think about that for a little bit. First of all, is it always true that for any undirected graph, there is a way to orient it so it's strongly connected? Okay? I claim the answer is no. Let's say that we took a look at this graph. Is there any way to orient the edges of this graph, okay, such that it leaves it strongly connected? And I say the answer is no. You're stuck. Because if you look at the center graph, center edge in this graph, suppose I orient it to the left. Maybe I could succeed in orienting these guys so I could drive around freely here. Maybe I could orient these edges so I could drive around freely here. But once I orient this to the left, I can drive from here to here, but there's no way to get back, correct? That this edge, the problem is once I assign it an orientation, the graph is no longer going to be able to be strongly connected. Okay, for this to be strongly connected, I have to be able to move both ways on that edge. Okay, does everybody see that? What about this graph over here? Can anybody see how to strongly orient it? So think about, maybe it's a good thing just to think about for a second. Look at this one. How would you assign edges to this, directions to this thing to make it strongly connected? So maybe think about that. Okay. So can this one be strongly connected by oriented appropriately? Okay, let's just maybe draw the example here. Okay, so it's something that looks like this. So here you go. How would we orient this one? Does anyone want to make a proposal as to how you would go about orienting this? Okay. Well, one idea I think I see people making a lot of circular motions with their fingers. What I think that they're saying is, what I could do is orient it so I have a cycle like that. Now I want to put other cycles here. This edge is now going like that. I want this thing to turn into a cycle also, right? So what direction do I have to orient this thing? Okay. Well, actually, I'm now going like this. This is the way that I've done so far. What do I have to do with this? I guess if I make this, one thing I could do is make this another cycle like that. And now everything's good, right? Would it be possible? What if I did this? If I made this one like that, is it possible for me to finish it up so that every edge is strongly connected? Yeah, in fact, for this case, but now I don't have any choice here, right? If I made it go like that, I'd be stuck. So like that, that would be fine. And what do I need to do about this? I could orient it either going around clockwise or counterclockwise. But I have to be consistent. Okay? And now then the thing is strongly connected. Does everybody sort of agree with that? Okay? Good. So what I want to now do is talk a little bit about how can we come up with a general strategy, a general algorithm to orient undirected graphs. Okay? And for this we're going to need to use two terms which are going to come up a lot when we talk about connectivity in graphs. It's the question of, we say that a bridge, okay, is an edge whose deletion disconnects the graph. Okay? So this, in the previous example, this was a bridge. Okay? An articulation vertex, okay, is a vertex whose deletion will disconnect the graph. Okay? So if we take a look at our previous examples, here we have an articulation vertex. If I delete this vertex, the act of deleting this vertex chops out chops out all these edges. Okay? This edge, this vertex, is now cut off from those vertices. Okay? An articulation vertex is a cut vertex, a vertex whose deletion disconnects the graph. A bridge is an edge that whose deletion will disconnect the graph. Okay? Any questions? Okay? Good. Well, first thing I'd like to claim is, or the first theorem I think I'd like to prove about this, is to claim that if you have a connected graph, an undirected connected graph, it can be oriented. It's orientable, meaning it can be oriented to be strongly connected, if and only if it does not contain a bridge. Okay? So let's think about this. Okay? First of all, it should be clear to you, based on our previous discussion, that in fact, if the graph does contain a bridge, then we're stuck. Why? Because if we have a bridge, okay, if we have a bridge being an edge whose deletion will disconnect the graph, by definition, we can only move across that bridge one way once we orient it. And so we can't move back the other way. Okay? So if your graph contains a bridge, okay, you shouldn't build it as a city road network. Okay? Is that clear? Okay? So again, if we look at our theorem, we've got an if and only if. Okay? If it does not contain a bridge, it is not orientable. Okay? If it does contain a bridge, it's not orientable. Now we have to show that if it does not contain a bridge, it is orientable. And that would suffice to prove the whole theorem. Okay? Does everybody agree with that? That there's two conditions we had to show for the if and only if. Okay? We now have to show that if I give you a bridgeless graph, okay, there is a way to orient it. Okay? Any questions? Well, to do that, I'm going to now give you an algorithmic proof. Okay? Namely, to prove to you that if there is a bridgeless graph, there is a way to orient it. The most convincing kind of proof would be one where you give me your bridgeless graph and I orient it for you, right? At the end, you look at this thing and say, yeah, it's good. So my algorithm is going to be as follows. You give me a graph, so long as that graph is not acyclic. What does it mean for a graph to be acyclic? Acyclic means without cycles. Okay? We say that a graph is acyclic if, basically it doesn't contain any cycles. This graph, certainly, an undirected graph, is acyclic if it doesn't contain any cycles. This is a connected acyclic graph, right? Okay? What are connected acyclic graphs called? Trees, right? A tree is a graph that is connected and has no cycles, right? So really what this is saying is, so long as the graph contains no cycles, means that it's either a tree or maybe it consists of disjoint components of a tree. Okay, maybe that are each of which are tree. This would be an example of an acyclic graph, right? Now, what do we know about a tree? Let's just think about some properties of trees that are interesting. If a tree is n vertices, how many edges if it has n vertices in the tree, how many edges does the tree have? Okay. How many edges does a tree on n vertices have? n minus 1. Okay. This is an important property of trees, maybe the most fundamental and important property of trees. How do you prove it? Well, just as a hand-waving thing, look, if I add another vertex, it requires an extra edge to connect it, right? Suppose I try to connect two things without adding another vertex. What happens? Okay, I create a cycle. It's no longer acyclic, right? So what I claim that this hand-waving argument proves is that any tree on n vertices has n minus 1 edges. Correct? Let's say here's my tree. Let's make it a kind of funny tree. So I've got n minus 1 n vertices, n minus 1 edges. How many of those edges on a tree are bridges? Just take a look at this thing. What is a bridge? A bridge whose edge will disconnect the tree, right? So how many of those edges are bridges? All of them. Bridges, every single edge in a tree is a bridge. That's why trees collapse when there's a storm, okay? Because anything that breaks the tree, okay? So that's sort of an important point to see here, okay? Any questions? Okay, good. Well, what is the algorithm again? We want to orient a particular graph, okay? The claim here is that I'm going to give you a graph, so long as it has a cycle, find a cycle in that undirected graph and orient it as a directed cycle. Then delete that cycle from the graph, okay? Then at the end of this loop, what is the condition under which I leave this loop? Means there's no more cycles to be found, right? Okay? Then my claim is between disconnected components of the thing, okay, use two edges, okay, to orient things in different directions. This is going to be sort of my algorithm, okay? So what is my algorithm going to be to take a undirected graph? You start out with this undirected graph. Say it's that. Let's say that it's this. Okay, here's an undirected graph. I'm going to take this cycle, pull it off and orient it in that way. Now I delete those edges. I now pull off another cycle. Okay, maybe it's this one. Orient it as that. Delete those edges. Here I've got another cycle. Actually, maybe I'll orient the cycle like that. Delete those edges. Okay. Now I'm going to take this one other cycle in the graph. I orient it that way. What edges, what do I now have? I now have a set of components in my graph and some edges I did not necessarily assign. What are the edges I haven't assigned anything to yet? This one, and this one. Correct? Okay. Any questions? So what is my situation? Within each component, if I now take a look at my graph, certainly within each directed cycle, every pair of points is going to be connected by a directed path, right? What happens if two cycles happen to share a vertex? Is every point from within one cycle accessible to every point in the other cycle? And I claim the answer is yes. If I want to drive from here to there, I may have to take the long way around, okay? But certainly, I'll get to the common point, okay? And will now be stuck like this. Now I claim I have what's left is now, I've got a bunch of connected components, okay? Each of my components of which are strongly connected. All I have to do to finish the job is orient these remaining edges. Now, what do I actually know? Okay? I know that the graph was bridgeless to start with, right? So what do I actually know? If I take a look at two connected components, there's going to be an edge. If the graph was connected, there had to be an edge linking those two together, right? Once I have one of those edges, because I know the graph was not bridgeless, that meant that the deletion of this edge did not disconnect the graph, right? Therefore, there had to be another path that I haven't yet considered. Okay, in fact, it just consists of this edge, which I can orient the other way. Okay? And therefore, I know that there's a way to stitch the thing up, okay, so as to, make the graph strongly connected, okay? I know that because the graph did not contain a bridge, there had to be, if there was one way to get, if I took an edge that connected two components, okay, there had to be another independent edge, okay, or path, and I orient in different direction that merges the two components. Finally, once I have all one strongly connected component, if there's any other edge that I haven't assigned, I can assign that either way I want. It's not necessary for this particular edge to be oriented one way or another to properly orient the graph. Okay? Any questions? Okay, so my claim is that in fact, once I have after I've completed cycles, I'm going to have disconnected components linked by undirected paths, and the paths had to work two ways. There had to be paths that I could use for both to and from, because I know there was no bridge in the graph. Any questions? Okay, good. So that tells us something. That starts to get us into the idea of strongly connected graphs. I think we now understand what strong and weak connectivity means. And again, the idea of directed graphs, paths in directed graphs, are interesting things. One structure that occurs a lot in computer science, okay, is the directed acyclic graph. A DAG is a graph, is I guess an acronym for directed acyclic graph. And in a lot of different contexts in computer science, you have what you would call a directed acyclic graph. Okay? For example, let's look at one application. For example, let's say we wanted to talk about, let's say, power. Okay, I don't know what we have. Let's say we want to model, let's say, power. Okay, and maybe this person over here, or fame, or something like this thing. Maybe this person here is less famous than that person. This person here is less famous than that person. This person here is less famous than that person. Let's say that this is Madonna, and this is Robert De Niro. Okay? Who here thinks Madonna is more famous than Robert De Niro? Some people. Who think that Robert De Niro is more famous than Madonna? Some other people. No one knows. Okay? So we can't say that one's more famous than the other. Okay? When you have a relationship where, where it's true that somebody, in a directed acyclic graph, okay, you have a world where every edge is directed, but there's no cycle in it. No directed cycle. Why would a directed cycle be bad in a famous graph? That means I'm more famous than you, you're more famous than me, and I'm more famous than you. That clearly makes no sense. That relationship makes no sense. So in a lot of situations, you have directed acyclic graphs, okay? Whenever you have, any kind of a hierarchy or relationship or something like that. And so DAGs are very important structures in computer science. Are DAGs strongly connected or weakly connected? By definition, again, it depends upon the DAG, okay? Some may not be either strongly connected or weakly connected. We could have maybe, two people like this, okay? That's directed. It's directed and acyclic, but it's not connected. But certainly a DAG can't be strongly connected because there's no cycles, directed cycles in it at all. Any questions? Okay. Good. Well, we talked about, so that's, I think, pretty much what I want to say about directed graphs and connectivity of directed graphs. The other facet of connectivity in graphs that's interesting, that's non-trivial or interesting, is for undirected graphs, the question of how connected something is. Okay? So we say that a graph is biconnected if it contains no articulation vertex. What was an articulation vertex? It was a vertex whose deletion would disconnect the graph, right? So we say that a graph is biconnected. We say that a graph is edge biconnected, okay, if it contains no edge whose deletion will disconnect the graph. We said that a bridge was an edge whose deletion would disconnect the graph. So saying something is edge biconnected is the same as saying something is bridgeless. Okay, correct? So, and you could think of, if you want to be sure, you could use the word vertex biconnected for this thing. But usually people talk just about deleting vertices instead of deleting edges. Okay, so that's why it's the default. We say that a graph, again, is vertex biconnected if it has no vertex whose deletion will disconnect the graph. Okay? Why is this important? Well, we talked about trees and how every edge in a tree was a bridge. Okay? what about a tree? Which vertices in a tree are, let's think about it. Which vertices in a tree are articulation vertices? Suppose I give you this tree. How many of the vertices deletion will disconnect the tree? Okay. The answer is only one of them, actually. Okay. It's not true. Deleting this won't disconnect it. Okay. It'll leave it, it sort of will leave a tree behind. Deleting this vertex in here will disconnect the tree, right? So when we talk about an articulation vertex, we mean a vertex whose deletion will disconnect it. Okay? And what's interesting in a tree, everything that is not a leaf will disconnect the tree, correct? So in any tree, you can just say that we say that a leaf in a tree is a vertex of degree 1. Okay? Any vertex in a tree that's not a leaf is an articulation vertex for it. Okay? Any questions? So what that tells me, though, is that trees have not only lots of bridges, they also have lots of articulation vertices in general. Okay? Which means, again, that trees are fragile. The reason we care about biconnectivity a lot, okay, or one important application of biconnectivity in graphs is in designing reliable communication networks. Okay? Suppose, let's say, that you had a computer network where all the traffic went through one central hub. Okay? Which node is most likely to break down by Murphy's law? Okay? The central hub. Okay? Which is the node that a smart terrorist would most likely go after if they wanted to disrupt your node, your graph? Okay? They do this thing, nobody can talk to each other. You blow up this guy, well, he's unhappy, but everybody else can continue to conduct business. Okay? How do you make a network more reliable? Well, you add more links to it. And ideally, you get to a situation where you add enough links, it's no longer the case that taking down any vertex will disconnect the graph. Okay? See this here. If I take this guy down, the rest of the graph can communicate. Take this guy down. They can all communicate through that path. Okay? So this gets us to a notion of sort of how connected graphs are. A graph that is biconnected, okay, or if you want to think bi stands for two connected, is stronger than a graph that is one connected. A graph that is one connected means that one vertex is necessary to disconnect the graph, which means it's a tree. Trees are one connected, excuse me. A two connected graph means that we have to delete at least two vertices to disconnect the graph. And in this particular case, you can delete these two, okay, and before it's disconnected. Okay? Any questions? Okay? So the notion of biconnectivity is good, okay, because it specifies more reliability than just saying it's connected. What is a zero connected graph? When we say a graph is zero connected, what does that mean? Okay, it means that if you delete zero vertices, the graph will be disconnected. So zero connected is another way of saying disconnected, right? It's disconnected to start with. Okay? Any questions? Okay? So graphs being biconnected have certain properties that make them interesting. First of all, of course, they're more reliable. But sometimes a graph has to be biconnected in order to have other properties that are interesting. Okay? So, for example, in soon we're going to talk about Hamiltonian cycles in graphs. A cycle in a Hamiltonian cycle is a tour that visits every vertex exactly once before coming home. Okay? So here, this graph here has a Hamiltonian cycle. I can go from here to here to here to here to here to here, right? Whereas another graph that, let's take a look at it. Let's put it like this. Let me just try it like this. Well, certainly, actually, does this graph here, actually, let's just try it like this. Is this graph Hamiltonian? Let's forget this thing here. Is this graph Hamiltonian? I don't believe it is, but let's just double check. Is it Hamiltonian? Actually, the answer is no, just because of this part, right? I can start out here. I can cruise from here to here. I can go there, but now I'm stuck visiting someplace I already visited, right? So there's no way I could visit all the vertices exactly once without passing. I have to pass through this vertex at least twice. Why is that? Well, that's because this is an articulation vertex, right? That if I delete this vertex, okay, then the graph is no longer connected. So it's certainly true that in order for a graph to be Hamiltonian, to have a cycle that visits every vertex, it has to be biconnected to start with, or else we can give up the show from the beginning. Okay? Any questions? Another property that's interesting, placed in algorithms certainly, where biconnectedness turns out to be important, is when you want to come up with a picture of a graph that is can be drawn in the plane. Again, we'll talk about planarity in upcoming weeks. But here is a graph which I'm drawing in a way that no two edges cross each other, right? This would be an uglier way to draw the same graph. Maybe I'd have an edge go there and there and there. Okay? In a planar drawing, no two edges cross. Okay? The interesting thing to see here is that if the graph has an articulation vertex, it's easier to draw in a planar way. Why is that? Well, if I have a planar graph, an articulation vertex, I could put that vertex down, divide my my paper into two windows, draw the stuff above the window, okay, and draw the stuff in the lower part of the window in this corner. So long as the vertex in common is on the outside, these two parts wouldn't interfere with each other, right? Is that clear? That you can break the thing at an articulation vertex, figure out how to draw each piece, and then figure out how to stick things together, okay? So here's an example where, again, finding a way to cut the graph into easily breaks it into pieces that's easier to deal with. Okay? Any questions? Okay? Good. So biconnectivity is important. Question? Can I explain? Good question. Good question. Can I explain the connection between biconnectivity and Hamiltonian cycles? Okay, good. A Hamiltonian cycle in a graph, and we'll talk about this more, okay, in the next week or so. A Hamiltonian cycle is a tour that visits each vertex in a graph exactly once, okay, and gets back to where it started from. So if I have a graph here, let's say now I'll have a graph that looks like this. Let's say it looks like this. This graph has a Hamiltonian cycle in it, okay? Namely, if I walk around the outside, right, I can visit every vertex exactly once, okay? Now, suppose I gave you, and testing whether a graph has a Hamiltonian cycle turns out to be a very complicated business. We'll talk more about that. But suppose somebody came to you and said, I have this very complicated graph. I know it's very hard to find a Hamiltonian cycle, but gee, is there any way, can you find me a Hamiltonian cycle in this graph? Okay? Okay? I can very easily show you that there is no Hamiltonian cycle in this graph. Why? Well, look at this vertex here, right? How is any Hamiltonian cycle going to look? Okay? Maybe it goes cruising through here. Somehow it's got to get back to the other side without using this vertex again. Well, this graph is not biconnected. Okay? That means it has an articulation vertex. The fact that it has an articulation vertex is enough to say it can't be Hamiltonian. Why? Because somehow I've got to jump over that vertex again. It can't do it without going through it because the graph is not biconnected. Okay? That's the connection. Any questions? No, Hamiltonian paths. A path would be a tour where I visit any vertex exactly once, but don't have to necessarily get home. Okay? So you could imagine a situation where I want to take a victory tour and visit all the cities and then relocate at the end to wherever I end up. I'm allowed to walk places and not necessarily get back to where I started from. A graph that has a path that visits all the vertices but doesn't get me back, that graph might not be biconnected. A good example of that would be, what if my graph looks like this? Here I have a path that visits all the vertices exactly once, but it's not biconnected. The moment I insist on having a cycle, though, that cycle gives me a biconnected graph. Any questions? Okay, good. Well, the important thing, okay, about graph connectivity or biconnectedness is that that's just sort of the start of a more general series of connectivity questions. Okay? We can generalize the notion of two connectivity to K connectivity, where we say that a graph is K connected if you have to destroy K vertices in order to disconnect the graph. Okay? So here we have a graph on 6 vertices that I claim has the property that it is 3 connected. Okay? In the sense that you have to delete at least 3 vertices in order to disconnect that graph. Right? Does everybody agree with that? I could delete these 2, but it doesn't do me any good. The thing's still standing. If I go chop, 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 now this guy can't communicate with that guy. Okay? So this is a 3 vertex connected graph, right? Because I can delete 3 to disconnect it, can't delete less than that. It's also a 3 edge connected graph, meaning that I can delete 3 edges and leave the graph connected. Okay, that if I delete less than 3 edges, the graph is still connected. What 3 edges can I delete from here to leave it disconnected? Okay. My claim would be the 3 edges associated with any one of these vertices, right? If I delete all these outside vertices of degree 3, if I delete those edges, the graph would be disconnected, right? Good. Here's a more interesting graph, though, that actually you should study for a while. Okay, look at this particular graph. What is the vertex connectivity of this graph? Let's maybe zoom it in just for sort of looking at it a little bit more. Whoosh. How many vertices do you have to delete to disconnect this graph? Okay. My claim is that you could delete 2 vertices, right? How many different ways could you delete 2 vertices to disconnect this graph? Okay. You could delete this one and this one and this one. You could also delete this one and this one, right? That would do the job, whereas this one and this one wouldn't. Okay? So here's a graph that is 2 vertex connected. Okay? How many edges do you have to delete from this graph? Great, to disconnect it. Okay? I think you'll all agree that 3 edges will suffice to disconnect this graph, right? If you blow away these 3 guys. Okay? So it's 3 edge connected. Okay? Any questions? But what's interesting about this one? The smallest degree vertex in this graph has degree 3, degree 4, right? These all have degree 4. This one has a degree 5, 4, 4. What's interesting here is that the ones that, to disconnect the graph, the edges and vertices don't seem to rely on the low degree vertices here. That's what's kind of interesting about this graph. The weakest part of the graph is not just chopping off a vertex. The weakest part of the graph is somewhere in the middle. Okay? Any questions? And so there's 3 different quantities that we have here that are potentially interesting. Okay? There's the degree, vertex degree. Okay? There's the edge connectivity. And there is the vertex connectivity. Okay? And we can see here that these 3 could all be different numbers. Right? Does everybody agree that those 3 are all different numbers? Is there any relationship, though, between the vertex connectivity, the edge connectivity, and the degree? Okay? I claim the following inequalities have to hold, okay, that you should think about and convince yourself of. Sorry, I'm playing with this a lot today. Suppose, let's say that we have the vertex connectivity is k, the edge connectivity is lambda, and the smallest degree is delta. I claim that the edge connectivity is less than or equal to the smallest degree in the graph. Does anyone see why that is? Why is it the case that the edge connectivity has to be less than or equal to the smallest degree in the graph? Okay, does anybody see it? It's not that complicated. Okay, can someone argue with me that the number of edges to delete has to be at most the smallest degree vertex in the graph, or vertex degree in the graph? Why? Well, I claim I could certainly give you in any graph a set of edges equal to the size of the smallest degree in the vertex. And that alone is enough to disconnect the graph, right? What if I want to make somebody a hermit? I find the one that has the fewest number of friends, okay? And then I either shoot the friends, that would be the vertex connectivity, okay? Or I plant rumors to lose these friendships, correct? If I have a vertex here of degree d, it suffices to cut d edges to disconnect the graph, right? So that tells me that connectivity has to be less than or equal to the lowest degree. Okay? It might be less than that, because it might very well be that there's sort of 2 chunks in the world that don't like each other, joined by one single friendship, even though with these countries everybody may know each other. Okay? So that side should be clear. What about the other side? Why is it the case that the vertex connectivity, the number of vertices you have to delete, has to be less than or equal to the number of edges you have to delete? Okay, let's think about that a little bit. Okay? Why is it that the number of vertices to disconnect the graph is less than or equal to the number of edges? Okay? Well, let's take a look at this thing. Suppose, let's say, I have a set of edges from S to T that will separate 2 vertices S and T, right? This may be all kind of garbled in here. There may be lots of edges, lots of edges. Okay? Suppose I have a set of edges here whose deletion will disconnect that graph. Separate S from T. What do I claim? I claim that, that I can delete one of these vertices associated with each edge. In the act of deleting this vertex, I will delete that edge and possibly some other ones, right? So my claim is that once you give me a set of E edges whose deletion will disconnect the graph, that means there has to be a certain number of, at most, that many vertices, E vertices, will suffice to disconnect the graph. Okay? How many people see that? Okay? How many people don't see that? Okay? It should be fairly clear. And so, in fact, we have these strict relationships between the edge connectivity, the vertex connectivity, and the minimum degree. Okay? Any questions? Okay? Question?
What is it most? How does it work with this lesson? You have three edges that connect the graph.
Yeah?
How would disconnect how would taking these two vertices?
Well, this is a less than or equal to, and not a less than, is the first thing to see. So suppose, let's say that I have a set of edges whose deletion disconnects the graph. By that it means there are two vertices, S and T, that can no longer talk to each other after I blow away those edges, right? Now what's the situation? Certainly, if there's a set of edges that will disconnect, whose deletion will disconnect S from T, then I know that at least one of the endpoints of each one of these edges is not S or T, right? Because, okay, so, okay. I mean, if we want to think about it like this thing, if there's a direct edge from S or T, okay, how many, this is actually the sort of one exception. If there's a direct edge from S to T, how many vertices do we have to delete to disconnect the graph? Well, you can't disconnect S and T, can you? Okay? So the only real exception here is the case of, a pair of vertices that are connected by one edge. But in general, the world that we have here is that if we have a set of E edges whose deletion will disconnect the graph, either those edges do not contain any vertex in common, or they might contain vertices in common, right? We could have a world like this, in which case bombing this one vertex is enough to take out all relationships between those parties. Any questions? Okay? Good. So it's interesting to think about this because a lot of problems in the real world that turn out, whenever you hear the word reliability in a network, somebody is talking about a problem on connectivity. Okay? And a lot of problems in the world that come up, really they're asking you questions about connectivity. Any questions? Good. What I'd like to show you is now one of the more important theorems in graph theory, okay, a famous, advanced, interesting theorem in graph theory called Menger's theorem, okay, that tells us how to test whether a graph is K-connected. Okay? So we should agree that to measure the reliability of a graph, it means to find out how many vertices will delete the graph. Do I have to delete to disconnect the graph? Okay? How do I do that? How do I characterize that? Okay? And what's interesting is there is actually an efficient algorithm to tell you how many vertices to delete to disconnect any graph. Okay? It's not an obvious one. Okay? And it relies heavily on Menger's theorem. So what is Menger's theorem? Okay? Menger said that in any graph Suppose I have two vertices, S and T, okay? And I want to find the smallest, then these are not adjacent. If they're adjacent, we agree. Adjacent means there's an edge directly between them. Then it's kind of hokey, okay? Because somehow you have to get at that edge, and you can't get at that edge by deleting anything. So suppose, let's say we have two vertices, S and T, that are not connected to each other, okay? And we want to find out what's the smallest number of vertices whose deletion will disconnect it. I claim that I could find that number by finding the maximum number of vertex disjoint paths between the two vertices. Okay? What do I mean by a path? Well, a path is just a chain. It's an undirected graph, so a path is just a walk from here to here. What does it mean for two paths to be vertex disjoint? It means they don't share any vertex in common, right? I claim this graph here. Actually, maybe I'll take a look. I'll draw it. Let me redraw the graph so I don't mess up my slide. Actually, let's just take a look at this may be more complicated than I wanted to deal with. My claim is this graph here has three vertex disjoint paths, mutually vertex disjoint paths from S to T. What are they? Well, I can take this path here, right? This path here has no intermediate vertices in common with any of those other ones, right? Certainly, if I have two paths from S to T, they both have to have S and T in common, so that doesn't count. But none of the intermediate vertices are shared, right? Is there a third vertex disjoint path that I can add to this thing? Certainly, I could either add this one or that one. Let's say I add this one. Now, is there any other vertex disjoint path from S to T? And the answer is no. Okay? What if, let's say, I add another vertex here? Is there a vertex disjoint path from S to T? No. Now notice there still is a path from S to T, but it uses a vertex we've already used, right? So this graph has three vertex disjoint paths, and I claim that that's the maximum number of vertex disjoint paths you can have, right? My claim here is that the vertex connectivity of this graph is equal to the maximum number of vertex disjoint paths that you can construct. Okay? And here, if you look at this thing, you have, I claim in this particular graph, there are three vertices necessary to delete those three vertices to disconnect S from T, right? Lo and behold, there are three vertex disjoint paths. What is the connection? Well, if you look at it, each one of these vertices lies on a different path, right? Okay? So that's going to be sort of the key idea here, that vertex disjoint paths are going to correspond to articulation vertices, or vertices whose deletion are necessary to disconnect the graph. Okay? Any questions about this? Okay? Let's prove Menger's theorem, or at least part of Menger's theorem. Okay? Menger's theorem is like any other graph theory theorem, an if and only if condition, if you want to think of it. If you want to prove that that the minimum number of separating vertices is the maximum number of paths, you've got to show me that if I have a certain number of vertices here whose deletion will disconnect the graph, then I can construct a certain number of paths and vice versa. Okay? The first thing I'd like to show you is that if I have k vertices sufficient to separate, whose deletion are sufficient to separate S from T, then in fact there cannot be K plus 1 vertex disjoint paths from S to T. Okay? Why is that? Suppose I have a graph here where there are K plus 1 vertex disjoint paths from S to T. Is it any subset of K vertices whose deletion will disconnect the graph? The answer is no. I can blow away one path only by deleting one vertex. So if in fact there's K plus 1 vertex disjoint paths, then darn it, I have to have K plus 1 vertices to delete to disconnect the graph. Okay? Does everybody agree with that? That part should be fairly straightforward. Okay? It shows that certainly the minimum number of separating vertices we've just proven is less than or equal to the maximum number of vertex disjoint paths. Okay? All we have to do is get rid of the less than or equal to and replace that by an equal to. Okay? But as in most graph theory things, that little bit is a lot more work. Okay? Maybe I'll go, let me try to show you, at least give you some flavor of that proof. Okay? Any questions? So what I'd like to now show you is, okay, that if in fact, okay, K vertices, but not K minus 1 vertices, separate S from T, then I would like to show you that in fact there have to be K vertex disjoint paths. Okay? I showed you that if you have K vertex disjoint paths, then you have to delete at least K vertices, okay, to disconnect the thing. I now want to show you that if you can delete K vertices, that K vertices are necessary to disconnect the graph, then in fact those K vertex disjoint paths have to exist. Okay? How do I do it? Well, we're going to prove it in a couple ways. First of all, suppose K equals 1. Okay? Suppose I have a graph where in fact one vertex will suffice to delete, to disconnect S from T. Does that mean that there is a path from S to T? Well, certainly. That's the definition. If the thing was connected before, then there had to be a path from S to T. Okay? And if you disconnect it, you'd better delete one of the vertices on this path, right? So for K equals 1, it's certainly true, okay, that if the graph is 1 connected, there exists one path from S to T. Okay? At least one path from S to T. Okay? Now, what if, on the other hand, it requires more than one vertex to disconnect the graph? Okay? Let's prove this by contradiction. Okay? And I just want to go through the structure of this proof, because it's representative of a lot of the contradiction proofs in graph theory. The way that you do things in a contradiction proof, okay, is that you sort of say, I'm going to prove to you something doesn't exist. Okay? Well, how am I going to prove it to you? I'm going to say, okay, it does exist. Okay? Let's now look at the smallest thing that does exist. Okay? If it exists, it has to look like this. And then I show you, but wait a second. If it exists, it can't look like that. So what's the conclusion? If it existed, it had to have this property and not have this property. Okay? That can't be. So the only way out of the dilemma is it never existed at all. Okay? And a lot of theorems in graph theory get proven in that style. Okay? And Menger's theorem is sort of an example of this. Okay? Any questions? You've probably all seen contradiction proofs, but that'll help you understand the style. What is the point going to be? Let's now say Menger's theorem is not true. What does it mean for Menger's theorem not to be true? It meant that there exists a graph, okay, that has connectivity k, but there does not exist, okay, k vertex disjoint paths in it, right? That's the counterexample. So if it's not true, there is that counterexample. Well, if there is a counterexample, then in fact there is a k for which it is smallest, right? We know it's not k equals 1. Maybe it's k2 or 3 or 76. I think it's 77. Okay, but some smallest k by which this is suddenly going to break. Okay? There is then going to be some graph for which it's not true, right? Let's say that f is a graph that for which it's not true, and what's more, f has the smallest number of vertices for which it's not true. Not only is it the smallest k, meaning it's the smallest number of paths for which it's not true, there may be lots of graphs, okay, for that k for which the theorem breaks. We're going to pick one of those graphs with the smallest number of vertices. Okay? Certainly, if there's a counterexample, there is such a thing. Further, once we now have this thing that is the smallest k that it breaks and the smallest number of vertices for which it breaks, I am now going to go and delete edges from this graph until I have the smallest number of edges for which it's going to be true. What does that mean? G is now going to be a graph, okay, where, okay, h vertices, okay, are necessary to disconnect it. It's got connectivity h, okay. This graph can be, but because it violates Menger's theorem, there is no more than h minus 1 vertex disjoint paths you can construct, right? That's what we know about about f. We're now going to delete edges until any edge we delete from now on gives us a graph whose connectivity is lower than that. Okay? Meaning that it's dropped, the connectivity is dropped from h to h minus 1. Notice what happens if I give you a graph and I start snipping edges out. Okay? The connectivity may or may not get lower. Okay, let's say I've got something like this. Suppose I now sit and cut this edge out. The connectivity didn't change, did it? The connectivity of this graph edge didn't change. Didn't change. The vertices are staying the same. The connectivity is now the same. But now I'm stuck. Any other edge I delete, I'm now doomed to lowering my connectivity. Okay? So the special case that I've set up here is that I've now got about as small a example as you can have. Okay? If the theorem's not true, there is a counterexample of this property. Okay? But my strategy is I've cornered it. So now I know exactly about as small a counterexample as I can have. Any questions? Okay. What I'm going to want to say is you can prove for any graph like that, and I would prove if I had a little bit more time, that this graph has two properties to it. Okay? Namely, there is no vertex adjacent to both S and T. So what is the case? Here's my smallest possible counterexample. Okay? So here I've got a lot of stuff like this. Suppose, let's take a look at it. Suppose I did have some vertex directly connected to S and T. Okay? What do I actually know? Okay? Okay, let me go show you the proof that the graph doesn't have that. Okay? If in fact there is some W vertex connected to both that, if I delete that thing, okay, then I claim that the separating set is going to be of size 1 smaller than it was. Why? Because I had a graph that deleting anything will reduce the size of the separating set. Okay? That means that the graph that I have after I delete it, okay, is smaller than the smallest counterexample, which means that it satisfied Menger's theorem, right? If it satisfied Menger's theorem, then the graph that I had here had a separating set of size h minus 1, but also had to have h minus 1 vertex disjoint paths, right? Because it satisfied the theorem. Well, what if I had h minus 1 vertex disjoint paths in here and a connectivity of h? What happens if I add this thing here? Now, to disconnect the graph, you got to go through this guy, right? And so you got to delete this one to disconnect the graph. But that also gives you another vertex disjoint path, right? So you couldn't have had this property be true if that was the worst example. Okay, how many people sort of see that? Okay, the other proof condition is a little bit more complicated, but basically it says that in any separating set of h vertices, you can show they're either all going to be connected to S or they're all going to be connected to T. Okay, right now you can believe me in this. Okay, suppose I show you that in the counterexample, that small counterexample, both of these conditions are true. What do we now know? Well, let's now take a look at the smallest path in our counterexample from S to T. Clearly there has to be one. What do we actually now know? This is S, this is T. There are some vertices involved, V1, V2, dot, dot, dot. Is it possible that V2, let's say we now know in this particular graph that all the separating vertices are either adjacent to S or T. By relabeling S or T, we can make S be the one that everybody's connected to, right? So here's my separating set. What do we know now? I know that U2, okay, is not adjacent to, what you call it, T. Wait, hold on. What am I saying here? Okay. That vertex 2 is not adjacent to T. Why is that? There is no vertex that is adjacent to both. Actually, let's just do it the other way. Excuse me. Sorry about that. Let's let T be the place where all the separating lines are connected to. I think this is the way around the dilemma. Okay. My first claim is that here I've got my path. Okay, S, U1, U2. U2 can't be connected to this one. Why? Because if U2 is connected to it, then I claim that we've got a vertex that's adjacent to both S and T. Okay? And actually this I'm now puzzling out as we run out of class. Okay? So let's assume that for now. Okay? X, let's say that we have an edge here from V1 to V2. This is going to be our edge X. If we delete this edge, okay, because we had a minimum example, okay, this graph now has to have a separation of H vertices. And we'll talk about H minus 1 vertices. My claim is that there is no edge from here to there, okay, because again, this edge is adjacent to that. That the separating set, okay, plus this extra vertex we had, okay, the separating set, after we deleted X, that edge, there was a separating set of size h minus 1. Therefore, the separating set plus one of those vertices was a set of h vertices that separated the thing. Okay? So therefore, we know that something about where those vertices are. Okay? But because to delete this extra edge, x, we could have deleted either this vertex or that vertex. So what is the situation? We've got a world where these vertices here, v1 and v2, cannot be, okay, adjacent to both of them, both x, s, and t, and yet deleting either one of them disconnects the graph. Okay, or deleting any one of them plus we'll delete that edge. So the cut set you get by deleting, after deleting that edge, okay, plus either one of those, okay, will be a cut set for that whole graph. Okay? So therefore there's a contradiction, which I guess is lost now in a fog, okay, that in fact that you have a situation where you have a contradiction about a property this path has. Okay? Again, read through it and we can discuss it if you wish. It's a messy kind of an argument. Okay, and I'll leave it at that. Okay? The interesting thing about it is as follows. Okay? First of all, it gives us a way of testing connectivity. Second of all, because it relates the problem of testing connectivity to finding paths through a network. In fact, using techniques from network flow, which if you might study in an algorithms class, you can find these separate paths. Okay, and that gives you a way to tell whether or not connectivity holds. Okay? Again, sorry the proof's complicated. Use it at least as a gross template of a, of a contradiction proof. Okay? And we'll continue with graph theory next class. Thanks a lot, and I'll let you go.